In 5.3, we're going to take a look at a couple specific formulas or patterns that can be used for some factoring, some specific factoring. I will say of the ones here listed, this first one is the important one. This is the one we will use time and time again, and to some extent it really boils down to you have to be able to recognize the pattern of a polynomial and know the formula that breaks it down through factoring. The other pair here, these are not as necessary as these will come from the easy case number game and bottoms up approaches if necessary. There's nothing unique about them. It's just a specific kind of situation, we'll say. But starting with this first one, the difference of squares. So x squared minus y squared, that pattern, difference, subtraction of squares, meaning each term is something being squared. If you have that pattern, then we know that breaks down to two binomials where the first terms are both x, the last terms are both y, and there's a plus and there's a minus between those two terms. Now this pattern here is a formula we actually would have seen back in chapter 4. The name of this pattern for this product was called the product of the sum and difference of two terms, meaning these terms are the same and these terms are the same, and we're multiplying together one addition and one subtraction of them. And again, the idea is that this x is that x and this y is that y squared in the original problem. So that's the form. I will say that my approach will normally involve using A and B. I like this just because capital A and capital B are letters you don't see as often in these polynomials we're dealing with. So I'm going to reference this form with the A and the B because what you're going to see is really it's just it boils down to identifying a pattern and identifying A and B and then knowing your formula to plug them into. As I mentioned, these other two up here, the perfect square trinomials, okay, well, they're a trinomial, and notice it's a pattern of an x squared, x no x, y squared, y no y, that fits that pattern that we saw in both of the sections with trinomials in section 5.2. The only difference is this is a very specific pattern because it comes from the squaring of one binomial. So rather than one binomial times a different one, you're saying x plus y times x plus y, or x minus y times x minus y, resulting in these very specific patterns. So we'll go through a couple examples because if you can recognize these, there'll be things that we will see throughout algebra where if you can recognize it and know that this is the pattern you're looking at, arguably it might be faster to just see it and know this form than go through a process like the number game or bottoms up to get here. Ultimately, these are not things you have to use though. They're just a specific form of factoring. So, starting with this first one. We're supposed to factor, so remember, no matter what we see here, first step GCF. GCF of these two terms is just a 1, so it doesn't do us any good. And so now, you're looking at two terms. And if you think back to the stuff we've learned how to factor, besides GCF that can apply to any size polynomial, we've not learned a process for two terms. We've learned trinomials, and we've learned the four terms, which we use grouping. So the only method we've got for two terms is this thing called difference of squares. Well, I see a minus sign, and so this question is, can we look at those two terms and determine what an A and a B would have to be for them to have come from squaring A and squaring B? I usually just put this off to the side like it's a question. The idea of, can I identify A? Meaning, what would I have to square to get P squared? Well, if A were P, then A squared would be P squared. Same question. What would I have to square to get 100? Well, if B were 10, 10 squared, B squared would be the 100. So you find yourself that A and B that fit the pattern, and then you just have to remember the formula, which is the A plus B times A minus B. And then you take your A and your B and plug them in. P plus 10, P minus 10, and that's factored. So that's going to be the difference of squares, just that process. Identifying the pattern, identifying A and B, plugging them into the formula. So question 2, got a factor, first step, GCF, and turns out this polynomial has a GCF. We see a 2 and an 18 with a 2 in common, and x cubed and x with an x in common. So we'll factor that out first, leaving us with x squared minus 9. Now what we're left with is two terms. We see a subtraction, And so that question again would be, can we identify an a and a b? Meaning, what squared is x squared? Well, if a is x, squaring x is x squared. For b, what squared is 9? That's 3. So it's basically like you're asking for the square root of each term, in a sense, to find these values. And so we know we've got the 2x out front, and then we know our difference of squares breaks down to x plus 3 and x minus 3. I will just mention this in terms of factoring. This is the form I write it in, a plus b, a minus b. If you wrote x minus 3 and x plus 3, you've got the same factors, something times something times something. The order you write them in doesn't actually make a difference, right? The order of multiplication, it's called commutative, where the order doesn't matter, but that's just gonna be the pattern I write it in, plus and then minus. All right, let's do some more examples. So we need to factor, so first step, GCF. Here GCF is a 1. We see a minus, so back to that question of what could a and b be. To square something to get 9a squared, just think of it piece by piece. To get the 9, you need a 3. To get the a squared, you need an a. To get the 16b squared, to get 16, you need a 4. To get b squared, you need a b. And now we can break it apart. Do our a plus b, a minus b, 3a plus 4b, and 3a minus 4b. And done. All right, next one. First step, GCF. GCF is a 1. So now we're looking at this thing, and we're going to say it has a subtraction sign. So let's try for an a and a b. So now, the question of what do you square to get y to the 4th? Well, thinking about our exponent rules, it makes sense that we would need y squared. Because y squared squared, right, a power to a power is where you multiply. So y squared squared would be y to the 4th, and b, you'd square 4 to get 16. So there's our a and our b. So a squared plus, or a plus b, oh man, I'm botching this. Y squared plus 4, trying to say one thing and write another, and y squared minus 4. Right, there's our a plus b, a minus b. Now, something we're going to look at throughout the rest of this chapter and various examples. And as we've seen before, just because you do one kind of factoring, just because in a problem we find a GCF, doesn't mean we're done. Well, we're going to start seeing just because we do a process doesn't mean we're done. With this process, this difference of squares process especially, we've been getting a lot of binomials as results of factors in these different problems. Notice right here, this y squared minus 4 is 2 terms with a minus in between. And if I asked for an a and a b for that pair, we could say a would be y and b would be 2. But now notice, this is a plus here. That is not something we're going to break down. The formula is specifically called difference of squares. So the y squared plus 4 does not get factored any further. But y squared minus 4, using that a and b, can break down to y plus 2, y minus 2.